Hello everybody. We're still talking about the function minimization, and we are giving an example here of one very famous um, application of this, and this is a very famous exercise actually, which is getting the radius of an insulation, or what we call the critical radius of an insulation. So to understand this problem, it's a very famous case actually when you have very hot or very cold fluid flowing inside a pipeline. So this is the pipeline. You're having a cross section, and you're looking as a top view here, and from here you can see the fluid flowing here, and this blue area is the cross section of the pipeline. So this is usually of a very conductive material, cast iron, stainless steel, whatever the material that you're using, and it's very conductive material. So the resistance of heat transfer of this pipeline is small, it's very thin, and it's very conductive, so it doesn't have almost any resistance to heat transfer. And that's why you have to put an insulating material, so that this insulation would prevent the heat from transferring from here to outside, or the other way if it's cold or hot. And to do this, you have to pick the insulation thickness, and to take into consideration everything, you have to think of heat transfer from here to here, as it is passing by two types of resistance: the resistance due to the insulation thickness, and by conduction, and the resistance by convection from the outer side of the pipeline to the air, or whatever the medium outside. And this is what we can describe here as the driving force divided by the resistance, and it's a very famous way of expressing the heat transfer from one place to another. And you can actually search in any heat transfer textbook, it will be there. It's a very convenient and very common way of expressing or modeling these heat transfer problems. So you have here two terms in the bottom, which is the resistance due to the conduction of insulation, and the resistance due to radiation. And this you can find the derivation in any heat transfer textbook. It's very simple. And this is R2, which is the outside radius of the insulation. R1 is the inner radius of insulation. L is the total length of the pipeline. And K is the thermal conductivity of the insulation. H is the heat transfer coefficient outside. Sometimes they put it as the convection heat transfer coefficient, and sometimes we put it as the combined heat transfer coefficient, which is the heat transfer that expresses the convection and radiation, so that you take both into consideration. So the point here is that as you increase R2, you are increasing the thickness of the insulation, and of course this will result in more resistance to heat transfer by conduction, and this will reduce the heat transfer or increase this term. And this is here, you can see R2 is in the numerator, and as this increases, the resistance or the whole term increases. And on the other side, if you increase this radius, then the area of heat transfer by convection increases, and therefore the convection resistance decreases. So you are giving the convection more area for heat transfer, and that's why this term is decreasing as R2 increases. And that's why the R2 will have different effects on both parts of the resistance to heat transfer. And that's why we need to know what we call the critical radius, which is the radius that would give the minimum resistance, so that we get away out of this, or do not pick this radius specifically. So we will do this here on oops, I'm sorry. On this problem here, we have here temperature inside is 320 Celsius, and outside is 5 Celsius, so it's very cold outside. This is the diameter of interest, which is the inner diameter of the insulation, or the outer diameter of the pipeline. And we know that K equals 0.05, and we know that H is 18. This is the combined heat transfer coefficient. So what we are going to do now, I'll just delete everything here so that we start just by the input. So you know that the L, I will do this for 100 meters. It doesn't matter 100 or 1 meter. It's not gonna be a problem. I know R1 is 0.025, and of course you need to make sure that all the units are consistent. I'm gonna pick the K of 0.5 for a reason, and I'm gonna get back to it at the end of the video, because it tells me here that K equals 0.05. I'm just use it as 0.5, and I'll get back to it. This is T1, T2, and H, and now I want to put my equation. So I know that R by conduction equals len, which expressed in Matlab as log. R, it's a function handle, so I have to first say that it is function of R2 log R2 divided by R1, and then divide this by, it was divided by 2 pi KL, 2 multiplied by pi multiplied by K multiplied by L. And now we will have R by convection, which is again a function handle of R2. It is 1 divided by 2 multiplied by pi multiplied by R2 multiplied by L multiplied by, it has to be uppercase, by H. And again, just to avoid any errors or messages that will show up in the future, and then R total equals, again it's a function handle of R2, R conduction of R2 plus R convection of R2. We can calculate Q, which is a function handle of R2, which is T1 minus T2 divided by the R total of R2. So now we have everything. What I want to minimize is not the R. What I want to minimize is the Q. So this is going to be what we call the objective function, which is the function of interest that I want to work on. Let's just I'll clear everything so I don't, or I'd better do it here. CLC clear and close, and now we want to do the fminsearch. But first I want to do one thing just to see how the resistance or the Q changes with the radius. So I would do first, and I like to do it a lot if I can, of course, because it's not always possible to do. So I will do the Q for radius of, the minimum radius is 0.025 up to 0.06, and let's see, I will run the file. So you can see here there is a peak. This is a maximum value of Q, and this is not what I want to get. And actually this yeah, I'm glad that I did this problem. So I want to minimize the Q, but actually I want to search here for the minimum value of resistance. So I will do this for R total, and I can do this on subplots 1, 2. So I'm trying to put everything together in or do what we did before with what we're doing here. So I'm gonna plot two plots side by side, showing how the resistance looks like and how the Q looks like as a function of R. So this is awesome. Actually, you can see there is a minimum value here of the resistance and there is a maximum value here of the Q. So I want to do the fminsearch on this resistance, not on the Q. I want to minimize the Q, but I don't want to I want to get the minimum R so that I can avoid it. So to do this, we will do the I would get two outputs here, the R critical, and I would get the value, and now I would see or use fminsearch of the function, which is, we said, r total, and the initial value I'd put it 0.025. From the plot I can tell that it is gonna be something between 0.025 and 0.03. And I would run the file now, and it tells me that it is 0.0278, which is this. And at 0.0278, it's something around 3.5 multiplied by 10 to the minus 3, which is exactly this. So we got the value pretty easily by doing the fminsearch, and it's matching what we got from the plotting with what we got from the fminsearch function calculations. One thing that is something that I tried to keep to the end is that I changed, and I didn't tell why I changed this to 0.5 instead of 0.05. When we go back here, you can actually, without using the fminsearch, you can do the get the minimum rate or the critical radius by getting this the derivative of this term in the bottom, and then put it equals to 0 to get the minimum value. And you can know that it equals to k over h. So if I do k h equals k over h, and I run the file, the k over h is gonna give you the same value as the r critical. So you actually do not need to for this specific case, it's easier to use k over h. I just use the fminsearch so that we can get an application. And if you do this calculations for k equals 0.05, it's gonna be 0.0028. Okay, this is k over h, and the plot will not show any minimum value at all. So 0.0028 is almost here. It's very, very small thickness. You are adding this is 2 millimeters of insulation, which is nothing, and actually it's not actually showing anything here on the plot, and that's why I use this 0.5 so that it's more obvious. And of course, if you use, let's say, 0.75, this is gonna be more shifted towards the right, because the k over h is a bigger value. And this is one good thing that gives you a physical understanding of the problem, and to know the weight of each one of these two resistances. So the weight of the resistance due to the conduction is very high if k is small, because this is small value, and this makes this whole term bigger. And you can even think about it physically without looking at the equation. If k gets smaller, then it's more resistive to heat transfer, and then it will have more bigger effect on heat transfer than convection. So as k gets smaller, the problem of the critical radius is actually not there. You wouldn't think about the critical radius if you are using a very insulating material with very, very low value of k. Even if h is higher but k is very, very small, that the k over h will be very, very small value, which is not even practical to use with the insulation or the insulating materials that people are using. Especially that people would put more or thicker thicknesses of insulation to account for the wearing or the effect of the air or rain or other things that happen. So it's usually not a problem if you are using a very insulating material. However, it was a very nice application of the fminsearch, and you can do it with fminbound as well. So I was happy that we were able to do this fminsearch on an actual problem, and to see or to compare what we did here with the plot to make sure that everything is matching. So I hope it was useful, and I'll see you in the next video, inshallah. Goodbye.